What's up, class? Evans here. Today's notes is about tolerances. And I know when you hear the word tolerance, you think like being politically correct and tolerating other people's views, which ironically is completely opposite of tolerance the way it's treated. But tolerancing here is engineering tolerance, where you're only going to tolerate certain dimensions and their sizes in order for something to function properly. So let's get right into the PowerPoint. So, why are tolerances used? Variation means changes in size. Variation is completely unavoidable, like you cannot prevent it from happening. Think about all those little cubes that we measured with dial calibers. When we measured those, we found that almost all of the cubes were of slightly different sizes. So you can't avoid the little size difference from one part you're manufacturing to the next. Even if you're in a high quality factory, it still is going to have some variation. Tolerances is telling you the control and the variation, that you won't allow certain dimensions outside of a variation. So since no two manufactured parts will be identical, there's always going to be a degree of variation. Tolerances are used in production drawings to control the manufacturing process and control the variation between copies of the same part. This is why when my car breaks down and I go and I buy a car part at a store, it will fit in my car because they know the exact size, they know the tolerances. And if it's a knockoff brand, you might find that things won't line up as well. Now that goes with anything where you can replace a part, even if it doesn't come from the same company. If you maintain the tolerances correctly, you'll avoid more and more defective parts. But there's a cost, literally a cost, to manufacturing something with very low tolerances. So let me move on to the next slide. There are two different types of tolerances: large tolerances and small tolerances. A large tolerance, it may affect the functionality of the part. Let me get anything. When this box is glued together, the machine that glues it all together, it doesn't have to be completely lined up. Like, it doesn't matter if the end of the box is a little bit crooked, if it's higher on one side than the other. It just needs to hold this thing together. That's it. That's all it has to do. So the tolerance on this box may not be such a big deal. My wallet over here. It needs to be toleranced so that cards can fit in here. But if you notice, they have room to wiggle around. So it can have a little bit of a tolerance that would be a large tolerance, and it would still fit credit cards and debit cards and IDs and stuff like that. That would still work, even if it had a large tolerance. So that's okay. This cell phone and this charger port, that's not wiggling around in there. That's fitting almost perfectly. This has a very small tolerance because I need this little thing to fit just perfectly in there and not pull out easily. So this would have a small tolerance. So let's talk about what that affects. A large tolerance might be for something that could be of lower quality. It could be for something that is less important, like that box that I showed you. It could be for something that is cheaply made, a knockoff brand. A small tolerance is going to make it more expensive. Now, it's not going to just make it expensive for no reason. It's going to make it expensive because you're going to have more precise manufacturing. When you manufacture this thing, if it's not the right size, it's not going to fit in the phone correctly. Well, actually, let me re-say that. It will fit in the phone correctly, but it won't last as long as it should be. So you get rid of it before it goes to the customer. And you don't want to have a lot of defective parts that don't match your tolerance, so you purchase higher quality machinery that can manufacture them. And you want to catch defects that go through, so you hire more people that can check things and make sure that they work correctly. Those would be like engineering jobs or higher paying technician jobs, because you're going to up the quality control. So a large tolerance can probably have cheaper manufacturing, faster manufacturing, um, cheaper prices. The dimensions can be off a little bit and it's not a big deal. You wouldn't put a large tolerance on something that was important. You would put it on things that are less important. Small tolerances would go to things that quality is very important. Things need to fit together just right. So we're talking about the components that meet up together when you assemble them, like bolt holes lining up in a car when you're connecting parts together. Things that need to be right on every time. That would be the smaller tolerances. Now that's to say, then, okay, then let's just only use small tolerances because it's always going to make a higher quality thing. Well, you wouldn't specify a tolerance that's smaller than necessary, because how much more expensive it becomes, how much more is in it in achieving that quality, it's not advantageous to only do small tolerances. You would have a mix depending on your. There are several factors that come into play why something would be expensive and something would be inexpensive. There's a lot of factors to play into why we have economic cars and we have mid-grade cars and we have luxury cars. A lot of it has to do with the features that are in those things. But tolerancing also plays a great role in that. Again, in a large tolerance, so if you hadn't written anything down, or if you have written down, you definitely need to write down this slide. And that is that a large tolerance, it has larger dimensional variation, it is usually lower quality, and it's usually low cost to the manufacturer. It's cheaper for them to manufacture. Why? Well, that's because they're using less expensive machinery and less quality control. Small tolerances. It has a smaller dimensional variation. It is usually superior quality, usually, but not a guarantee, but usually it would be. Usually super expensive, I see the S in expensive, to manufacture. Why? More expensive machinery is going to be bought, more quality control is going to be needed. Again, you won't specify a tolerance that is smaller than necessary, because it becomes more expensive. You don't give it a tolerance just out of nowhere. It's typically calculated and not just arbitrarily chosen. The video I have here, BMW Quality Management, if you look up that title, or if you go into the comments below, you should find that video attached. It's a pretty good video. It talks a lot about tolerancing. You can see some of the tools that they use to check the tolerancing and the quality control, and you can see how they're willing to reject parts that don't match up to what they want. And that's part of the reason why BMW is expensive, but also part of the reason why they last well. Okay, so let's get a definition down of a tolerance. A tolerance is an acceptable amount of dimensional variation that will still allow an object to function correctly. That's the key part. Function correctly. Now, a smaller tolerance might function correctly longer. A larger tolerance might function correctly shorter. But function correctly nonetheless, that is what it's doing. It's not tolerating things that will cause it to fall apart. Heck, this is the reason why we have different warranties, a 90-day warranty, a 5-year warranty, a lifetime warranty. They're not going to back it with money if they didn't put their name on it to last that long. Because if they're going to give it a lifetime warranty, I promise you that they put tolerances on it to achieve that goal. And that they're saying if it didn't last a lifetime, we're going to replace it because we engineered it to do so. So that's why you might see warranty differences. There are 3 basic tolerances that occur most often in working drawings. So this is the way that they are marked. So one would be a limit dimension. A limit dimension shows the upper and the lower limits of something. 2 is a bilateral dimension. Now, if you notice, I'm highlighting them there. So the one that says 980 and 975, it's saying that that dimension can only be between 0.980 and 0.975. If it's anything outside of that range, reject the part. Bilateral tolerance, the one at the top, it says it's 1.17 plus or minus 0.002. 0.002 is the thickness of a hair. Remember, that's very small. It's like the thickness of a sheet of paper. So whatever fits inside of here, if it doesn't have the tolerance to match it, it won't fit in there correctly. Now remember, it might work, but it might also fall apart too early. And if you are going to warranty something, it needs to be able to last the time at which you gave that warranty. So these tolerances are there to protect those warranties and make them work correctly. Unilateral tolerance. So if you notice in this one, it's different than all of them. Uni means one, so unilateral means it only goes in one direction. So in that example there, we see it's a 1/2 inch plus 0.005, which would be about 2.5 hairs, but minus nothing. Like it can be 1/2 inch and a little bit more. Why couldn't it be less? Well, whatever fits in this slot, if it's less, it won't fit in there correctly. If it's too much, it will end up sliding and wiggling back and forth and wearing parts away till they don't function correctly. So here's a limit dimension again. It provides an upper and lower limit. Any size between or equal to the upper limit or lower limit is allowed. It has to be in between these. So this is a limit dimension. It's saying that there is a very small dimensional variation in this part. And if you don't know what that actually is an axle, a side view of an axle, probably not in a car, more like in a lawnmower or something like that. And in the axle, in order to attach like gears or spinning objects to the axle, they don't typically clamp them on there, though sometimes they might. But if you want to have a higher quality thing, what you do is you take your like the axle, and I know this isn't a circle or anything, and you cut a groove into it, and then when you attach, like, let's say, and none of these things are what I say, you come and attach like your gear on it, then you cut a slot in the gear and you put a softer metal in between the gear and the axle. And what that does is it allows the gear and the axle to spin together. And if you were to strike anything like let's say in a lawnmower, you're pushing your lawnmower and you hit like a rock, which I've done this before, like your water meter or something, you hit it, that force that hits the blade is going to push up into the engine and break it. It'd be better if the softer metal, which is this little square shape here, were to break, and that way it would separate the rotation of the spinning blade and the spinning axle. And so you would want that key, which is just like a little kind of brass rectangle prism that's sticking gears and axles together. You would want that to be a very precise fit. You wouldn't want that to be loose, else it wouldn't serve its purpose. And you don't want it to be too tight, else it won't fit correctly. So that's why the limit dimension here is like giving only a limit of like 1/2 of a hair there. So it's like no movement in the size of that. Bilateral, bi means two. If you notice that it has a plus sign, that is a plus or minus sign. That means it has two directions it can go, both an up and a low. It does the same thing as a limit dimension. The limit dimension gives the upper and lower dimension. The bilateral tolerance gives the desired dimension plus any kind of play in the size. So it provides an equal variation, both larger and smaller, upon the size that you actually are trying to achieve. Notice the plus and minus sign. A unilateral tolerance gives the dimension that is desired and a little bit of play in one direction, not in the other direction. It's uni, meaning there's only one direction in which the dimension can change. So in this case, it could be slightly smaller than desired, but not, slightly larger than desired, because it could be point. So according to this could be 0.00, 0.001, 0.002, 0.5003, 0.5004. It can't be 0.5005, and it cannot be 0.499. It has to be between 0.5 and 0.504, and all the numbers in between there. So that's a unilateral tolerance, where it allows in one direction of change, but not in the other. Remember, the entire purpose of the tolerance is to allow it to function for the time that you want it to function. And if it falls outside of those tolerances, it probably will not reach its warranty life. And it's not like if you put a 30-day warranty on something, you're designing it to break after 30 days. It's not necessarily true. It may last for years, but the whole purpose of the warranty is to protect more of the company than you when they give it like a 30-day warranty. If they give it like a 5-year warranty or more, then you probably have a higher quality part and better dimensioning. Let me skip that. Now, one more definition to point out. This is a specified dimension. I kind of mentioned it earlier. We want it to be 1.5, but the bilateral tolerance allows it to go up and down in one direction. Now, when we're talking about tolerancing, you also need to think about limits, an upper limit and a lower limit. So I've kind of already mentioned it several times. An upper limit would be take the specified dimension and add the positive variance. So 1.5 plus 0.05, that's 1.55. A lower dimension would be subtracting them. That would be 1.45. So if you wanted to find the upper and lower limit, I think it's pretty straightforward. Just understand the terms: limits, upper limit, lower limit, specified dimension. It's a little bit more what I'm pointing out. I'm sure you can add and subtract things and figure this out on your own. So ultimately, what the tolerance ends up being is you take the upper limit and you take the lower limit. The upper limit being 1.55, lower limit being 1.45. If we were to subtract those, that would be 1/10 of an inch, or 0.10. So the tolerance is 0.10. Tolerance is the total variance in a dimension. So the tolerance isn't 0.05 or plus or minus 0.05. The tolerance is actually 0.10, 1/10 of an inch. Here's just kind of a graphic showing that distance. You could write that equation down. I would suggest that tolerance equals upper limit minus lower limit, and then write the example if you want, so you can see what a tolerance means in terms of math. Another type of tolerance is a general tolerance. So, and my face is a little bit in the way there. I fit up there. All right, so a general tolerance is a tolerance that is assumed if there's no specific tolerance is given for the dimension. So you might just have a general tolerance covering the entire drawing. Now it will cover the entire drawing unless, of course, there was a specific dimension on or specific tolerance attached to a dimension. Let me show you just an example. So here is a drawing. We have it's a plate with 3 different holes in it, and then the holes are all specified what they are. If you notice, like this has a tolerance of plus or minus 0.003, but the diameter doesn't have a tolerance. This has a limit dimension, but the upper hole doesn't, but the bottom one does. So you might see that there's a couple of different, like none of these have tolerances. This doesn't have a tolerance, but this does. So you might notice that there are some dimensions that are toleranced and some that aren't, but ultimately they all are because they have a universal tolerance here, or I mean a general tolerance. So that 0.3 or 3.00 that doesn't have a tolerance on the drawing does have a tolerance connected to it here in the general tolerance. Because it has 2 decimal places, that communicates to what type of tolerance should be attached to it. So that means it is plus or minus 0.01, which means this could be 3.01 or it could be 2.99. So the tolerance would be 0.02. So that's the reason why sometimes things have different length decimals at the end, because it might be connected to a specific tolerance. I mean a general tolerance because it doesn't have a specific tolerance. All right, pause the video and write these 3 down: clearance fit, interference fit, and transition fit. Okay, you paused it, you wrote them down. Let me explain them. A clearance fit A clearance fit is it limits the size of mating parts so that the clearance always results when mating parts are assembled. Clearance means there's space, right? When you go to a store that has a clearance store, they're clearing out Christmas so they can bring in New Year's. They're clearing out Christmas so they can bring in Valentine's Day. The clearance means there's space. I've got this hinge here. This is an example of a clearance fit. See how they can rotate within each other? If you've ever had like a toy car where the wheel can spin on the axle, that's a clearance fit. The axle fits, the wheel fits on the axle, and then the wheel can spin on the axle. So there's a little tiny bit of space between the wheel and the axle so that it spins freely. Not so much that it's wobbling, and not so little that it's not moving correctly. An interference fit, this is a fit where there is no space and it's being forced together. I think I had, oh yeah. My best example for that would be like a hammer and a nail. When I take a hammer and I nail it into a piece of wood, this nail didn't have a hole that was put in there. No, it's just forced into that wood. It's forcing in between the grain, squishing in there. This is a harder material. This is a softer material. And if I pound that further through, it won't rotate or anything like that. Now, actually, come to think of it, this right here is both an example of a, so this is an example of a clearance fit and an interference fit. If you look, you see that little mark that I just drew on it? If I rotate this hinge, notice how the bolt spins with it. That is an interference fit. This bolt is a larger size than the diameter of the inside of this side of the hinge because the bolt rotates with it. This side, it doesn't rotate with it. It is a clearance fit. It's allowed to freely move over this bolt. So this is a clearance fit because it freely spins. Interference fit, it's stuck to that bolt. A transition fit, I don't think I have a good example of that, but that would be where a part could be either an interference or a clearance fit. It's kind of in between and it can go either direction. I don't have a good example for that. Main ones would be clearance fit and interference fit. If you've got a minute or so after the video, I encourage you to look up this title. The video will be posted in the comments below. And this is a company talking about shafts that they sell, and they talk about different types of fits and tolerances that they use. So it's kind of an engineering video. So let's look again at clearance fits and interference fit. If we look at this wheel and axle here, the wheel can be as large as 1025, but as small as 1015. This axle can be as large as 10, but as small as 9.29, which means that this axle is smaller than the inside diameter of this wheel, which means it's a clearance fit that the wheel can freely spin on the axle. Interference fit, that means there's always interference between the axle and the opening. So in here, the axle is 10 and as small as 9.92, same size, but this wheel is as big as 9.90 and as small as 9.85. Notice that the inside diameter of this wheel is always smaller than the axle, which means it's going to kind of squish over the axle and it will spin with the axle. As opposed to a clearance fit where the wheel spins freely on the axle. Interference fit, the wheel and the axle spin together. This is a good way in order to make things where they where you don't need glue, like on a car where the wheel and the axle spin together. That means I didn't have to glue the parts together. The axle and the inside diameter of the plastic wheel were designed in such a way where the plasticity or elasticity of the wheel squished onto the axle. Let me skip that. skip that. Allowance, get down the definition of allowance. That's the last one to write down. Allowance is the minimum clearance or maximum interference between parts. And we'll look at that in an assignment for next week. So the allowance here is the largest this can be is, or smallest that the wheel inside diameter can be is 10/15, and the smallest, the largest that this axle can be is 10, giving an allowance of 0.15. So we're taking the smallest of the wheel, but the largest of the axle. In this last one, we have an allowance with the interference fit. We're still using the smaller of the wheel and the larger of the axle. And if you notice, it gives us a negative 0.15. So it goes in the opposite direction. So trying to summarize everything, don't know why that means summary and hand motions. In general, the more specified the dimension, the tighter the tolerance, or the smaller the tolerance. Overly precise dimensions and overly tight tolerances increase manufacturing costs. Specified dimensions only to the precision and tolerance necessary for the part to function properly. The large and small tolerance, and that is that a larger tolerance has a larger dimensional variation, lower quality, low cost to manufacture. A small tolerance has smaller dimensional variation, usually superior quality, and usually super expensive manufacturing. That would be the difference between a large and a small tolerance. It's a bit of a complicated subject, but it is very engineering, and it's something that engineers use often, and we'll practice it next week as I go over a worksheet with you. I hope all is well. Don't forget to comment on the posts if you have questions. Don't forget to turn in your assignments. There's no assignment to turn in with this one because we're going to do a worksheet next week on it. Bye.